Welcome back, Night Owls. This is Dr. Nighttime. And tonight, we're going over problems 3.1 through 3.7 from the SOA official problem list. Chapter 3 had a total of 13 recommended problems in it, but I don't want to do more than 10 problems in one video, or else it will become a little too difficult to navigate to the one problem that someone might have been struggling with. So I'll do 7 in this video, and then 6 in the next one. So with that out of the way, let's start with problem number 1. You're given an excerpt from a select and ultimate life table with a select period of 3 years. Now, you might recognize this table as the one I used for the last couple of examples in my Chapter 3 lecture video. I said they were using it to ask one particular problem. Here's the one particular problem they want to ask. Deaths follow a constant force of mortality over each year of age. Calculate 1,000 times 3Q selected at 60 plus 0.75 years later, deferred 2 years. And so when you're looking at this, first thing you should do is you should look at this Q probability and try to think about how old is the person right now, and over what time window are we asking about the person dying. Person is 60 3/4 years old. So we can say age 60.75. And thinking about the person dying between age 63.75, age 62.75 and 65.75. Notice that for age 60.75 and 62.75, we have to think about the fact that this person was selected at age 60. For 65.75, we don't. We can just use the ultimate figures. And so that's what we do. Notice that for any of the quarter years, it says constant force of mortality. So when we're looking 3/4 of the year in, we're looking at figure for the next year to the 3/4 power times figure from the beginning of the year to the 1/4 power, and multiply those together. Standard, constant force of mortality, geometric mean. So here are the numbers we get. Here's the algebra. Crunch our numbers together, we get 0.1167. It asks for 1,000 of that, so 116.7 rounds to 117. So, to recap, you see this problem, you look at this Q figure, this deferred Q figure, you think, how old is the person now? And what's the time window where this person would die that we're interested in? And then you also have to use your knowledge of select and ultimate models, right, and select life tables, and the constant force of mortality assumption to figure out what your probabilities are for those fractional years. Yes, you also know that when you're selecting at age 60, right, so for 60.75, you're looking at somewhere between this 80,000 and this 79,000. For 62.75, you're still looking at the selected at 60 line. So you're looking between 77,000 and 74,000. And for 65.75, you're looking at something between 67,000 and 65,000. Okay. Problem 3.2. You're given the following extract from a mortality table with a 1-year select period. In other words, they don't tell you the everything that goes into the table. And they tell you deaths are uniformly distributed over each year of age, and they give you the complete expectation of life for a selected 65-year-old, and you have to calculate the complete expectation of life for a selected 66-year-old. Because everything is in whole years, we want to convert from complete to current, right? When you have annual tables like this, you can only calculate stuff nicely with curtate. And that's the first step. They gave you complete, you calculate curtates. Because deaths are uniformly distributed over each year of age, you always get curtate equals complete minus 0.5. So you get curtate of selected at 65 is 14.5. Use the recursive formula for expectation of life. You'll notice P selected at 65 was 0.96, right? Because if you started with 1,000 and 40 died, don't look at this 955, right? That's not the same cohort. This is not the same cohort that was selected at age 65. You look at this 40, you realize that you had 960 survivors, right? 1,000 minus 40. And so 960 divided by 1,000 is 0.96. Plug that in to the recursive formula, and you get E66. Then you can use that, plug into the recursive formula again, to get E67. How do you... So for that, you need P66, right? Well, again, we have to fill in this blank here. We started with a 955, we subtracted 45, that means this has to be a 910. So you have this 910 over this 960. And that gets you E67. Finally, you use the recursive formula again to get E66. Get that it's 14.2. Sorry, E selected at 66 is 14.2. And then circle E selected at 66 is the curtate E selected at 66 plus 0.5. That gets you 14.7. So, to review, you're given an annualized table, so you have to do most of your work in terms of curtate, not complete. And you had to convert from E selected at 65 to regular E of 66 to regular E of 67 back to regular E selected at 66. So you had to use the recursive formula 3 times. Forward twice, and backward once. Next one. An excerpt from a select and ultimate life table with a select period of 2 years is given. Deaths are uniformly distributed over each year of age. Calculate 10,000 times Q51 plus 0.5 deferred, 2.2 Q51 plus 0.05. Or selected at 51 plus 0.05, or plus 0.5, there we go. Yeah. Alright, this is actually a relatively straightforward one. The only difficulty is these fractional years, but again, you look at this and you ask, how old is the person right now? 51 and a half. But not just any 51 and a half year old. Someone who's selected at age 51. So, for our total population, we want something between this 97,000 and this 93,000. And since it's exactly halfway between, we're at 0.5, we know the denominator of our fraction is going to be 95,000, right? Halfway between these two. Then you ask, over what time period are we interested in the person dying? That is from right now to age 53.7. You'll notice since it's a 2-year select period, 53.7 selected at 51 is in the ultimate period. And I'm hovering over the wrong ones. It's this one, between 52 and 53, right? 50. Sorry, no, I had it right the whole time. 53.7 is going to be between age 53 and 54. So hovering over these, right? You want something in between these two. And you crunch your numbers. And get 0.1074. And since it asked for, what was it, 10,000 times that? Yeah, so you want 1074. Choice E. Next one. The SULT Club has 4,000 members, all age 25, with independent future lifetimes. The mortality for each member follows the standard ultimate life table, hence the SULT Club. Calculate the largest integer n using the normal approximation such that the probability that there are at least n survivors at age 95 is at least 90%. So to solve that, you look at the standard ultimate life table. Here I actually have the selections. Note, I won't always, so for this chapter, I'll highlight the individual selections and put the little boxes around the appropriate numbers. In future chapters, I'll assume you know how to do this. But we look at the tables. If we want the probability of one person surviving from age 25 to age 95, you get 21,178 over 99,871. It's 0.2121. The expectation of x is 4,000 times that, or 848. The standard deviation, hopefully you remember standard deviation of a binomial distribution. Crunch the numbers here, and you get 25.85. If n is the number, n what you're looking for, okay, the critical value you're looking for is 1.282. And so you crunch the numbers and you get 815. Problem 3.5. You're given the following life table. Let A be 2.5 Q60 deferred 3.4 years, assuming uniform distribution of deaths. And let B be 2.5 Q60 deferred 3.4 years, assuming a constant force of mortality. Calculate 100,000 times A minus B. So for that, you just calculate with uniform distribution of deaths. Right? Either way, you're going to get L63.4 minus L65.9 divided by L60. Right? You use standard thing where you ask, how old is the person now? And over what age range am I asking about the person dying? Calculate your life numbers. And you get that A ends up being 0.27778. With CFM, you're calculating B. You're looking at the same probability, you're just estimating it a different way. Crunch your numbers. You get B is 0.27672. Again, we don't need to estimate L60 anymore. We have that just from the table. A minus B is 0.00106, multiply by 100,000, move the decimal point 1, 2, 3, 4, 5 spaces, you get 106 as your answer. 3.6, you're given the following extracts from a table with a 3-year select period. And you're told the current expectation of life for a 64-year-old is 5.1. Find the current expectation of life for a 61-year-old. Sorry, for someone selected at age 61. And so, yeah, we have to do this 1 year at a time. We're looking 3 years in advance, right? Person is currently selected at age 61. And we have to figure out, we have to relate that to somebody who was 61 3 years ago. Notice that you're in the ultimate period now. So you can say, well, we can work backwards. 1 year prior, you're 63, but selected at age 61, so bracket 61 plus 2. Do your 1 year recursion formula. Get that a year ago. Current expectation was 5.246. Do it a second time. Get 5.496. Do it one more time. Do it one more time. To get E selected at 61 is 5.847. Lastly, problem 3.7. For a mortality table with a select period of 2 years, you're given an excerpt from the table, and now they're asking about constant force of mortality. Calculate 1,000, 2.5 Q selected at 50 plus 0.4. Again, how old is the person now? Person is 50.4, selected at age 50, so you're somewhere between here and here. And when will the person, what time period are we worried about the person dying? Between now and age 52.9, which put you here. So to solve this one, I would assume a radix of 1,000. You're always allowed to assume a radix of however big you need. We would get the death probability we're looking for is 1 minus the survival probability. Notice that age 52.9 is outside the select period, so we don't need brackets here. And so then we just say, all right, what's the probability of, all right, how many of these 1,000 people would survive to age 50.4, assuming they were selected at age 50. So then L 50.4 will be 1,000 to the 0.6 times 995 to the 0.4. And then L 52.9, you start with these 1,000 people. You say 0.995 for surviving the first year, 0.9937 for surviving the second year, and then 0.9920 to the 0.9 for surviving 9/10 of the third year. Gets you 981.6. Crunch your numbers together, and you get a death probability of 0.0164. It wanted 1,000 times that, so that gets you the choice is 16.4. Alright, that's it for those 7 problems. I hope you found this useful. And as always, if you like the way I explain things and want to arrange private lessons, click the link in the description below. And until next time, this is Dr. Nighttime wishing you a good night.